You know that from the first revolution we got a lot of innovation, mainly driven by steam power and steam engines. And then later on we got the same with electricity and a lot of electrical power devices. And the third industrial revolution, it's a little bit less concrete. It has to do with the transition from analog control to digital control. And a lot of things that we have now, a lot of things that we are anticipating to be within the fourth industrial revolution, we have inherited from technology, digital control, from the third industrial revolution. The fourth industrial revolution is a little bit special because of that. We cannot pinpoint one single key enabling technology. It's rather a convergence of many different technologies, and at the moment, it has mainly a philosophical value. It's not much more than that. And it's a vision propelled by the idea of the creation of real-time connected world based on cyberphysical intelligent objects. Well, this is a mouthful of words. So what does this mean? It takes actually three ingredients to create a cyberphysical object. It takes the physical object itself, and it takes any form of a computer, and it takes the connection between these two. But this we knew already. This we knew from the third industrial revolution. This is how our factories are working today. Okay, we have a lot of computer-controlled equipment. We have a lot of communication already between this computer-controlled equipment. What it's really new is that now we are creating a cyber representation, a kind of an intelligent layer on top of this whole. And this intelligent layer, it's really important because objects will start to do things not because they are programmed to do so, but because they are programmed to choose what they want to do. They are programmed to interact with other objects. They are programmed to learn automatically about other objects. So one robot will know that another object is interacting with. It's a robot, or it's a human, or it's a station. And therefore, that object will adjust automatically. It will know what to expect from that other robot, from that other human, from that other station. And this is really new. And there's a massive amount of research really required to bring these visions through. But this is what it's all about. This is really the vision. Then we can take a bunch of these objects. We can put them together and we can create a system, an intelligent cyber-physical system that has a lot of these objects cooperating together. And when we think of it, we are already taking the first step with the creation of smart objects, smart cars that will be able to drive autonomously, connect to the cloud, extract map information, pre-schedule repairs, understand when they will break down. So a lot of consumer products are already or will be in the near future generating value in other systems. What we often forget is that the resources that we have inside the factory, they can be themselves intelligent objects. They can themselves extract and collect information. They can generate value out of that information. And they will be someone else's products. So this is really the vision of the smart factory, a fully connected world, an Internet of Things world, where these intelligent objects can, for instance, understand that another object they need to cooperate with has failed. And they will know, okay, that other object that failed was a robot and it was carrying out a specific process. So I know how to adjust to that. But if it's not a robot, if it's a human, the object will adjust in a different way. So this is really what it's all about, creating this additional layer of intelligence that massively improves the dynamics of our systems. So this is really a knowledge-based system. Objects are actively mining, creating, manipulating more knowledge, and continuously adjusting, continuously learning from what they have extracted, from what they have learned. And that information is automatically feedback. And this means that there will be other sources of knowledge as well. For instance, these systems, at least we expect them to be so adaptable that they will extend the useful life of our human resources. People will be able to work longer, will be able to work better because they are supported by the system. So these human resources will also contribute with more knowledge to the system. So in a way, everything is tangled. All the information that the smart factory produces generates value to create better products, which generate more knowledge, which is feedback to the system again. And this is a little bit the vision. Everything is connected, everything it's really tangled, and these objects are actively and constantly learning. So this is really the vision. The big question now is how far are we from this? And there is a lot of initiatives that are pouring money onto this. In the US, there's the industrial internet that is being committed to the creation of the network infrastructure that can handle the deluge of information that these new systems will generate. In Europe, we have the Factories of the Future initiative that has been supporting the research on the factories of the future, on the smart factory for so many years now. And in China, we have, and this has been recently announced, the Made in China 2025. And this is the Chinese government saying that they want to step up their production, not in terms of quantity, but in terms of quality. They want greener, more connected, more efficient factories. And of course, in a subset of Europe, we have Industry 4.0, which is the German initiative that, in one way or another, it's what has triggered all these discussions. So everyone is talking about Industry 4.0 because the Germans are talking about it. And this is an important point. It's not by chance, because really Industry 4.0, it's the most comprehensive program, the one that has designed the better vision for what is a smart factory. This is why we are all talking about this, and this is why we all, in one way or another, refer to Industry 4.0. But although these initiatives are very, very recently, it is important to note that a lot of research has been carried out before. So Industry 4.0, it's a relatively recent phenomenon, but there has been research on this for the past 10 to 15 years, and a lot of good research. So I just want to share with you some examples from my own personal experience that show to an extent how far the community, the research community, has been closer to the creation of a smart factory based on this idea of intelligent objects, intelligent services, and cyber-physical systems. So the first thing, it's really the creation of a cyber-physical industrial component. And this means we need to turn a robot, a station, an operator into one of these intelligent, highly dynamic entities. And the good news is that we already know how to connect systems to a network. So this is not a big deal. Just to give you an example, and this is interesting because this is something we are doing here with Yaskava Nordic. And this is work carried out by some of my students at LiU. This is the remote control using Wi-Fi of a Yaskava robot. So this is really the first step, making the object available online. So when he presses the button, it causes the robot to move. It's wireless. And this is really important because now, using that computer, we can place the cyber part of that robot pretty much anywhere. It can be inside the robot controller, it can be in a cloud, it can be in our own computational infrastructure, local servers, it doesn't matter. But we have the required infrastructure to create the cyber object now. So there's already a lot of previous and excellent research on how to do this and on how to connect that. Of course, we need to work on some security issues. Okay, this is using communication protocols that are not entirely safe, and security, as we unfortunately know nowadays, it's really a pressing issue. So we need to be a little bit calm about putting a lot of systems out in the cloud until security is a little bit better understood. But nevertheless, we can't stop research because of that. The other interesting problem here is how to maintain this cyber-physical relation. As I said, we can have the intelligent part of this robot living pretty much anywhere. So this will depend from system to system where we really have it. And the other thing is that, and I will come to this later on, very few people really know how to design these systems, and we are starting to educate our students a little bit in this direction. So the really difficult part here, it's the part that we don't see. It's the part that is stored inside that computer and that is going to make that robot understand that it's going to cooperate with humans, other robots, other systems, etc. So if we put this together, we can create a cyber-physical intelligence system. And I have another video to show, but before I play it, I would like you to look beyond what seems like a normal system. Okay, that looks like a standard automation system, but really everything, it's a completely independent and intelligent object. Products are intelligent products, and they act as clients of the system. So they go around and they ask the system where the different resources are, which resources are available for them, and they actually contain their own knowledge of how they can be produced, of how they should be manipulated on that system. Let me get this going. Okay. There it goes. So each one of these pallets contains an intelligent product, and you have to imagine these objects are interacting not because they are told so. They are dynamically negotiating, they are dynamically finding about other resources. And this enables us to do dynamic changes to the system while the system is running. For instance, there we can just unplug and plug things to the system without any reconfiguration effort. When we put the new head on that station, that cyber-physical object will wake up and announce that, hello, I'm here. I know how to do this task for you. If anyone needs me, come and find me. And of course, this is a rather simple change, but we can take it to the next step. We can actually take the entire station out and put it somewhere else on the line and have the system adjusting automatically to that. And again, the system is doing so not because it has been pre-programmed to do so, but it has been designed in the way that it can handle these disturbances, it can handle these changes in a rather dynamic way. So of course, it requires the usual mechatronic interfaces. But then there's, again, the part that we don't see, the cyber part, that it's really the part that is putting it all together. So it's connecting and disconnecting and making it work. We had it from Industry 3.0, making sure that it works again without any reconfiguration, that it's instantly plugged and produced. This is something that it's the cyber part, it's the new part, taking care of it. So somewhere in the system there will be a product that is looking for this station. As long as we put the station in place, the product will know about this, will find about where the new station is. We'll go there and execute. And we have a lot of reference architectures that tells us how to design these systems. And we can plug and produce with extremely small ramp-up and setup times. All of this, it's because the objects are not working because they are told to do so. They choose to do so. They have that autonomy. They are able to reason on what's best for them and what's best for the system. Of course, the problem is that there are so many different contributions at different technology readiness levels that it's sometimes difficult to understand what it's what. And we have been very successful in managing the connection between the smart factory and the smart product, while the product is still inside the factory. Once it leaves the factory, there's currently no concept for that. And when we look at Industry 4.0, these are actually two different separate directions. Some people are going for smart products, other people are going for smart factories. But the connection, it's really important because it adds more value. And of course, everything that you saw, there's no really at the moment standard industrial technology for that. The good news is that it is possible to connect these systems in a way that it is relatively system independent, okay? In this system, we integrated components from many different vendors, from many different shapes, many different sizes. And this is because when we design such a system, we focus on the cyber part, on the intelligent part. We don't focus on the fact that it is a robot, or it is a human, or it is a station. We focus on the functionality that it provides and how these objects, these generic objects, could interact with each other. And let me give you another example of what can be done with that. So there in the video, we have a mix of a of the physical system with a completely virtual system. Once that product goes in there, it only has an existence on the physical world. But that simulation, it's really interfering with the physical system. So the entire infrastructure that controls this, it's both independent of the physical part and independent of the virtual part. It's above that. So if we want to replace the virtual part, we just disconnect that computer and put the station instead. And it works because we are not changing the control rules. We are not changing the perception that these intelligent components have of each other. We are just changing the hardware. We are just changing the equipment that they are manipulating. And this is quite interesting because even simple objects can be turned into cyber-physical objects and can generate value if we connect them in a meaningful way. Of course, we always need a little bit of additional computation power, and there will be many different strategies for integrating this. But it is possible to do, and the overall integration effort, it's really minimal, even when compared with what we are doing today. This is just to give you an idea about previous research. We recently got an EU application approved. It's called Open Dynamic Manufacturing Operating Systems for Smart Plug-and-Produce Automation Components. So this is something starting now, a very ambitious project that aims at creating the infrastructure for the smart factory on a quite high TRL level. But the important part here is that all the concepts, they are coming from a set of completely different projects where we were involved before, our partners were involved before. So although we are thinking about the fourth industrial revolution as something new, there is a lot of previous and significant research that relates to that. Some of these projects, they date back in time more than 10 years, and they created the basis for distributed intelligent control, self-awareness, intelligent autonomous components, distributed control, self-optimizing systems, systems that can optimize for energy consumption, that can selectively switch off components, sensor enhanced and self-diagnostic models, so on and so forth. So there's a lot of previous research that it's much older than what we now think it's Industry 4.0. And finally, because and this is something that it's very dear to me and very dear to us at the division, these systems, they are more complex. They are more multidisciplinary. So there's a need for educating future engineers on how to understand these systems, on how to design them, on how to conceive them. And we started this year this course called Emerging Factory Technologies, where the students really build a cyber-physical system from scratch. And this is the result, and this was entirely built by students with a little bit of my help, sorry. Let's get this going. So again, I would ask you to see beyond the conventional system, because the product there, it's an autonomous entity. Each conveyor, it's an autonomous entity. And what you are seeing, it's really several components negotiating and interacting because they understand each other, because they know how to communicate with each other. And because they are able to do so, we can do what we are going to do next, which is we can reverse the position of the stations. And without doing any reprogramming, any reconfiguration, the product will also run, will continue to run, because the only thing that they really need is to know that the resources that they need from the system are there, and that they know how to locate them, they know how to communicate with them. So this is something that, this was done entirely by mechanical engineer students with very, very little IT background. So I think this is quite impressive for them to be able to pull such a feat. And internationally, we have also started the summer school on intelligent agents in automation. We are the founders of this summer school, and we are very proud to be hosting it this year at LIU. So when I come to think of this, when I come to think about the full picture and what does this might mean for Sweden, I think in Sweden we have an excellent environment for collaborative research, and this is an excellent head start. And we also have collectively the technical resources to pull this through. but they are separated. They are in many different places, and people are not necessarily aware of the competencies of each other that could be highly complementary. And it is an opportunity now, actually, because although Germans have started the initiative, a lot of work has been done before. And there is a lot of highly skilled people out there in Europe that know how to design these systems. And the other good thing is that research on this area is relatively inexpensive compared with other areas where we have more fundamental research. So it's mainly about advanced computing technologies, advanced software programming, IT infrastructure, so on and so forth. So it's relatively inexpensive. The problem is that the concept is not yet fully understood by everyone. And there are a lot of key players confusing the individual technology readiness levels of certain technologies with the required readiness level of the aggregation of this technology, which is really what is going to power the fourth industrial revolution. And of course, here in Sweden, this is now the time to start thinking about this, because the rest of the world, either in an explicit or in an implicit way. So I gave you examples from the US, China, in Europe, but we know that Canada is doing more or less the same thing. Not explicitly, but there are internally calls for projects in this area. And all the member states in Europe are doing the same. Japan has also funding on this. India has also funding on this. So this is starting to be a global phenomenon. So now it's probably the last chance to catch a seat on the front row. The other major threat is if companies think that this is something that they are going to buy as a turnkey solution rather than putting some of their time onto this. I'm not saying that companies should start now massively developing software or IT, but they should own the information models that are relevant for them. They should be the owners of that knowledge. They should be the owners of the models that might generate value for them in the future. Otherwise, they might be held hostage by their system integrators that will have the monopoly of that core knowledge. So I'd like to finish this with one final thought. I think now we are predicting the fourth industrial revolution. I think that in many years from now, when we look back, we will see that there was not a really key enabling technology. Information was really the key enabling technology, and the way we handle that information was really the key enabling technology powering all this exciting movement. And that's all for me. Thank you so much.